everyone. We are from Group 5, and today we will be presenting and we will be solving 6 questions regarding some operations over here. But first of all, let us introduce ourselves. My name is Kenia Regatha Siahaya, but my student ID is 2415101073.
And my name is Indra Pandika with student ID 241510101. So for the first question until the question will be answered by me. Okay. So the first question is explain the reflection operation operator and explain table 1 and table 2. Specifically, how to obtain the standard matrix and complete one appropriate exercise. Okay, so the reflection operation is a linear transformation that maps every vector to its mirror image with respect to a line in R2 or a plane in R3 that pass through the origin. Okay, first we can explain about the table number 1. Okay, so here we have operator reflection about the x-axis. So here we have the general equation. Transform t of vector x and y equals x point minus y. So the image of E1 and E2 will be 1 and 0 minus 1. So the standard matrix will be 1, 0 and 0 minus 1. And the second is reflection about the y-axis. And general equation is transform t x and y equals minus x and y. So here we have to change the value of x from 1 to minus 1. So here, as you can see, the value of E1 will be changed from 1 come to minus 1. And the value of E2 not changed. So the standard matrix will be minus 1, 0, and 0, 1. So number third is reflection about the line y equals x. So the general equation is x point y equals y point x. So here we have to swap the value of the x and y. So here in E1 we got the value 0 and 1, and E2 is 1 and 0. So the standard matrix will be 0, 1 and 1, 0. Okay. For next, we can explain the table number 2. Okay, so the first we have the reflection about the xy plane. So we have general equation which is transform t of vector x, y, and z equals x, y, and z. So here we have to change the value of z. So in image of E1 until E3, we can change the value of E3 from 0, 0, 1 to 0, 0, minus 1. And the value of E1 and E2 not change. And the standard matrix will be like this: 1, 0, 0, 0, 1, 0, and 0, 0, minus 1. The second is reflection about the xz plane. And we have the general equation is transform t of vector x, y, and z equals x minus y and z. So here we have changed the value of y from plus to negative. So we have to change the value in E2 from 0, 1, 0 to the 0, minus 1 0, and the standard matrix will be 1 0 0, 0 minus 1 0, and 0 0 1. The last is reflection about the YZ plane, and we have the general equation is transform T of vector x, y, and z equals minus x, y, and z. So here we have to change the value of x. So you can see in image of E3 we have the change of element from 0 0 1 to 0 sorry, I mean we have the changes the element of E1 from 1 0 0 to minus 1 0 0. So the result of the matrix will be minus 1 0 0 0 1 0 and 0 0 1. Okay. So for the next, we will practice question in exercise 4.9, number 1. So the question is use matrix multiplication to find the reflection of minus 1 and 2 about the x-axis, y-axis, and find y equals x. So the first, we can answer x-axis. So to find the reflection about x-axis, we have to multiply the standard matrix from x-axis, which is so to answer the to find the reflection about x-axis, we have multiply the standard matrix of x-axis, which is minus 1 and 2 multiplied by the standard matrix of x-axis is 1 0 and 0 minus 1. So the result will be minus 1 and minus 2. So here the reflection about x-axis is minus 1 and minus 2. And second is reflection about y-axis. So same as before, we have to multiply the vector with the y-axis. So the vector is minus 1 and 2. And multiply by the minus 1, 0, and 0, 1. So the result will be 1 and 2. And the last question is transform from line y equals x. Okay, so for the find the representation of y equal x, we have to multiply the vector with the standard matrix of y equals 0. Sorry, I mean y equals x. So the standard matrix is 0, 1, 1, and 0. So the result is 2 and minus 1. Okay. For next, we can answer the question number 2. Okay, so the question number 2 is explain the projection operator and explain table 3 and 4. Specifically, how to obtain the standard matrix and complete one appropriate exercise. Okay, so we will explain about the table number 3. Okay, so here we have operator orthogonal projection onto the x-axis with the general equation is transform t vector x and y equals x and 0. So in E1 we have the value is 1 and 0, and E2 is 0, 0. So the standard matrix will be 1, 0, and 0, 0. And then the second is orthogonal projection onto the y-axis. So the general equation is transform x and y equals 0 and y. So in this we have to change the value of x from 1 to 0, and the value of E2 not change. So the standard matrix will be 0, 0, and 0, 1. The second, we will explain the table number 4. Okay, so the first we have orthogonal projection onto the xy plane with the general equation is transform t of vector x, y, and z equals x, y, and 0. So in this we have to change the value of E3, and the value of E1 and E2 not change. So the standard matrix will be like this. And then the orthogonal projection onto the xz plane with the standard general equation is transform t of vector x, y, and z equals x, 0, and y. So we have changed the value of y. So the value of E1 and E3 not changes, and the value of E1 will be changed from 0, 1, 0 to 0, 0, 0. So the standard matrix will be 1, 0, 0, 0, 0, 0, and 0, 0, 1. And the last is orthogonal projection onto the YZ plane with the general equation is transform t of vector x, y, and z equals 0, y, and z. So here we have to change the value of x. So the value of x from 1, 0, 0 to 0, 0, 0, and the value of E1 and E3 not change. So the standard matrix will be like this: 0, 0, 0, 0, 1, 0, 0, 0, 1. And then we can... Okay, for next we will answer the question number 5 in exercise 4.9. Okay, so the question is use matrix multiplication to find the orthogonal projection 2 and minus 5 onto the x-axis and y-axis. So first we can answer the x-axis. Okay. So to find the orthogonal projection from this vector using multiplication, we have to multiply the vector this with the standard matrix of x-axis. Okay. So the x-axis is 1, 0, 0, 0 multiplied by the vector 2 and minus 5. So the result will be 2 and 0. And question number 2 is the orthogonal projection from y-axis. So same as before, we have to multiply the vector with the y-axis. So the y-axis is 0, 0, 0, and 1. And multiply by the vector is 2 and minus 5. So the answer is 0 and minus 5. Okay. So maybe that's our explanation from question number 2. Next, we can answer the question number 3. Okay. So the question number 3 is explain the rotation operator and explain table 5 and 6. Specifically, how to obtain the standard matrix and complete one appropriate exercise. Okay. So the operator rotation is a linear transformation that rotates every vectors v in R2 and R3 around the origin by a specific angle theta. So the first we can explain the example number 5. Okay. So here we have counterclockwise rotation about the origin, source, and angle theta. So the rotation equation will be y1 equals x cos theta minus y sin theta, and y2 equals x sin theta plus y cos theta. So the standard matrix will be cos theta and minus sin theta and cos theta. Okay. Next, we can explain about the table number 6. Okay, so here we have operator. The first operator is counterclockwise rotation about the positive x-axis toward an angle theta. So the rotation equation will be y1 equals x, y2 equals y cos theta and z sin theta, and y3 I mean w3 equals y sin theta plus z cos theta, and the standard matrix will be 1 to 0, 0 cos theta sin theta, 0 sin theta and cos. And the operator number 2 is counterclockwise rotation about the positive y-axis toward an angle theta. So in rotation equation, we have to change the element of y2. So the element of y2 will be y. So the standard matrix will be cos theta, 0 sin theta, 0, 1, 0, minus sin 0, 0, and cos theta. So the last one is counterclockwise rotation about the positive z-axis short angle theta. So that means in our second equation we have to change the value of y3 to equals z, and the standard matrix will be like this. Okay, so for the next we will answer the practice question number 9. Okay, so the question is use matrix multiplication to find the image of the vector 3 and minus 4 when it is rotated about the origin through an angle of theta equals 30 degree, theta equals minus 60 degree, and theta equals 45 60 degree, and the last is theta equals 90 degree. Okay. Okay. For the first, we can use the standard rotation matrix like this. We use the standard rotation matrix like this. Okay. And then we know the standard matrix, we can we can substitute the value of 30 degree to the standard of matrix. So we can substitute cos 30 minus sin 30, and here sin 30. And here cos 30. And then we have to find the value of cos 30 and sin 30. So cos, the value of sin 30 is 1 over 2. 1 over 2 cross root of 2, and the value of minus sin 30 is minus 1 over 2. And here 1 over 2, and here 1 over 2 cross root of 2. And then we have to multiply by the vector 3 and 4 to find the rotation matrix. Okay, so the result will be 3 over 2 cross root of 3 and plus 2. And 3 over 2 minus 2 cross root of 3. Okay, and next we can find the rotation of angle 90 degree. So same as before, we have to substitute the value of 90 degree to this standard matrix. Cos 60 minus sin 60, and here cos 60, and here sin 60. Okay, so the value of cos 60 is 1/2, and the value of minus sin 60 is minus 1/2 cross root of 3. Sorry, I mean 1/2 cross root of 3, and here is minus 1/2 cross root of 3, and here minus 3, I mean 1/2. So the result will be so after that we have to multiply by the factor here. Factor is 3 and minus 4. The result will be 3/2 minus 3/2 minus 2 cross root of 3 and minus 2. So this is the result from question number B. Next, angle equals 45 degree. So same as before, we have to substitute the 45 degree to the standard matrix. Okay, we can find the value of cos 45 is 1/2 cross root of 2, and the value of sin 45 is 1/2 cross of root 2, and this minus 1/2 cross of root 2, and here 1/2 cross root of 2. and then we can multiply by the vector is 3 and minus 4. So the result will be 3/2 plus root of 2 and 1/2 root of 2 and 3/2 cross root 2 and minus 2 minus 1/2 cross root of 2. Okay, and the last one is angle 90 degree. Okay, so same as before, we have to substitute the value of 90 to the standard of matrix. So the value of cos 90 is 0 and the value of minus sin 90 is minus 1, and here 1 and here 0, and then we have to multiply by the vector is 3 and minus 4. So the result will be 4 and 3. Okay, so maybe that's an explanation from me. For the next session will be continued by Kenia. Thanks.
So we will continue with the fourth operation, which is dilatation and contraction. So here we have two tables, which is table 7 and table 8. So first of all, let's talk about the operators. So the operators and dilatations and contractions are all on the scale of Rn. T, Rn, given that T x is equal to Kx. And with scalar K is more or equal than 0, meaning that if K is more than 1, it means that it is dilatation, as you can see over here. And if it is 0, less or equal than K, and K is less than 1, let's see here, you can say that it is a contraction. So, in table 7, we can see that it shows the effects on R2 operator, but the operator being T, X, and Y, T, X, and Y, like here, that is equal to Kx and Ky for square unit, where each point are multiplied by K. And then, in table 8 here, it shows an analog in the form of R3. The standard matrix for R2 are diagonal with K and diagonal like this, K0, 0, K. But for K3, it will look like this one here. So to get it, we only need to find the standard basis of EI, then make it into a column matrix. So in order for us to get the standard matrix, we need to say that dilatation or contraction operator are defined as this, as T, X, y equals to kx, ky. So to get a standard matrix, the procedure involves, first, we need to write the standard basis in R2. So the standard basis in R2 is E1 equals to 1 and 0, and E2 equals to 0 and 1. And here, we will find the image of each basis. So for E1, have this T E1 equals T1, 0 equals to K multiplied by 1 and K multiplied by 0. This results in K0 like this. And then for this, we have TE2, which T01, and then we got 0, 1, then multiplied with K. So K multiplied by 0, and then K multiplied by 1. This will result in 0K. So now we need to arrange both of these into a matrix. So A, T, E1, and T, E2 is as seen here. Now, this is how we get the standard basis. The standard matrix. Now, in order for us to get the form in R3, it also requires these same steps there. So, let us just go ahead and answer some example question, which is from page 268, 269, which is exercise 13A. So the question involves use matrix multiplication to find contraction of -1, 2, but the factor of k is 1 or 2, 1 over 2. So t, let's go ahead and solve it. T equals 2. So we see that our standard matrix is like this. So we just need to insert k into that. So we get 1. We got half, 0, 0, half, and we can go ahead and just multiply that with our question there, and then multiply it, and then we will get half multiplied by -1 plus 0 multiplied by 2, and we get 0 multiplied by -1 plus half multiplied by 2. Now this will get minus half, negative half, and 1. This is the contraction. Okay, that is for contraction and dilatation. Next, we will go ahead for the fifth, which is expansion and compression. So expansion and compression, we have table 9 over here. Okay, so the operators in expansion and compression multiplies only one coordinate with the factor k. For example, in R2, expansion or compression in x direction is txy equals to kx and y. Here, an x direction, we have txy, and it becomes kxy. In y direction, over here, in y direction, we have txy equals to x ky. So here we can see that it only multiplies one coordinate with the factor k. Now, if k is more than 1, then it is an expansion, like this. But if we see this, which is 0 is less or equal to k and less than 1, it is a compression. So, Table 9 shows illustration and standard matrix for compression or expansion in the direction of x and y in R2. So, in compression and expansion in x, we can see that the standard matrix is like this. Meanwhile, for the compression or expansion in y, we can see that the standard matrix is here. Now, each of these use the same method to find TE1 and TE2, then to arrange the columns. So, let's say how to find the standard matrix over here, okay? Let's go ahead down here. Standard matrix. Okay, so let's start to look for the x direction. So for the x direction, the standard base of E1 is 1 and 0, and E2 is 0 and 1. Then we will find the base image, which is TE1 is equals to K1, 0, and we get K and 0. TE2, we go to K0, 1 equals to 0, 1. So next we just need to arrange the columns so we get K0 and 0, 1. That is how we get the standard matrix for x direction. So it's the same as this one. Then we will go ahead and find the y direction. We also do the same process as this one. The only difference is that it becomes like this. TE1 becomes 1 and 0, and TE2 is then we get column matrix as 1, 0, and 0, K. Just like this one. Okay, so now let's go ahead and do the practice question, which is from exercise 17A, page 200. So here we are asked to use a matrix multiplication to find the compression of -1 and 2 in the x direction, with the factor of k equals to half. So here we can go ahead and just use the matrix standard that we have found there, which is k0 and 0, 1, and replace that with the factor. So half, 0, 0, 1. And then the x is -1 and 2, so we just need to multiply that, and then multiply that as normal, and we will get minus negative half and 2. So this is the compression. Okay, so that is for the fifth, which is compression and expansion. Let's move on to the last procedure, which is shear. Now shear uses the table 10 here. This is shear. And shear is basically shifting. So a shear shifts parallel points one axis in a proportional distance to other axis coordinate. Now two forms in R2, and shear to the direction of x with factor k is Txy equals to x plus ky and y. This is in the direction of x. In the direction of y, we have shear to y with the factor k, which is Txy equals to xy plus kx. So if here we have y, here we have kx here. So it looks like it's reversed, but it's not exactly reversed. Okay, so let's go ahead and see the table here. So in the table here, we can see that the x-axis is horizontal, meanwhile in the y-axis direction, it is vertical. So it shows that we see before transformation and after transformation, and we have the standard matrix over here. Okay. So, in shear to x, the shift happens horizontally, and the distance is comparable to y coordinate. The operator is Txy equals to x plus ky and y. This means that if y is 0, then Tx0 is equals to x0, or the point of the x-axis is unchanged. But if y is not 0, then the points will shift as far as ky to the right. And then for the vertical or y, okay, so in shear to y, which is vertical, the shear to y means that the point shift happens vertically in the y-axis, and the distance is proportional with the x-coordinate. So the operator is this one here, and the meaning of this is that if x is 0, then the t0y is equals to 0y, which means that the y-axis is unchanged. So if we have x is 0 here, and then we will get t is 0 to y, this means that the y-axis here is unchanged. And if x is not 0, this means that the point shifts as far as kx or upwards. And upwards is if k is more than 0, or downwards if k is less than 0. So this one is upwards and this one is downwards. And I forgot to mention that if in the shear to horizontal, if the k is more than 0, then it will shift to the left, to the right, and if the k is less than 0, then it will shift to the left there. Okay, so let's discuss how to get the standard matrix. So to get the standard matrix to x, we will use basically the same method as the last two operations, given that Txy is x plus ky y, and we have the standard basis, which is we have the standard basis, which is 1 and 0, and E2 is 0 and 1. We can continue and find the image, which, given that E1 and E2 is like this, we'll go ahead and insert this one here. So we will get T E1 to 1 plus K times 0, this, then we'll get 1 and 0. And T E2, we will get 0 plus K 1, then we will get k and 1. Now arrange the columns into 1, 0 and k1. Then we will get this. Okay, now to y. And to y, we will do the same thing but with the over here. So let's just go ahead and insert it all. But E1 is 1, 0 and E2 is 0, 1. We'll insert it with T. E1 is 1, 0 plus K times 1 equals to 1K. And then T, E2 is 0, 1 plus K times 0, which we will get 0, 1. And then we will get the standard matrix, which is 1, K, and 0, 1. Just like this. Okay, now that we're done with the standard matrix, let's go ahead and do a practice question. In order for us to do the practice question, we'll get this question over here. I'm going to use 1 there to x. So given shear operation to x with factor of k equals to 3, and to x, that means we will use this x plus ky, y. We will find t to 1. Find the standard matrix and find a point image. Okay, so let's go ahead and start with the standard matrix. So the standard matrix we already have is 1, k, 0, 1 like this. So we'll go ahead and insert here. 2 will be 1, 3, 0, 1. Okay, we got it. The standard matrix. Then we will find t. In order for us to find t, we will just go and do this. Equals to 2 plus 3 times minus 1, 1. And then we will get 2 minus 3, 1. And then we will get minus 1, minus 1. That. And then for C, which is finding the point image, we will find a point image of 0, 1, 1, 1, and 2, 0. So to find this, just go ahead and do the same thing, which is 0 plus 3 times 1, this, then we will get the point image is 3, 1. And then t, 1, 1, 1 plus k, which is 3, 1, 1, and then we get the result of 4 and 1. And for t of 2, 0, 2 plus k, 3, and then multiplied by 0, 0. We got 0, 2, and 2. And there it is. This is for the shear in the direction of x. Okay.
So because we had explained everything here, starting from the first table and all the way to the 10th table, we have reached the end of our discussion over here. So with this, we hope everything is clear and understandable. We are from Group 5. Thank you for watching.